I think everyone can hear me or not. Let me, I think.
Okay.
Okay. So let's start. First of all, thank you for having me here. Today I will give you a tutorial on one of my fields of research, which is on data-driven predictive maintenance. I split this tutorial into parts. This first part, it's more about concepts, challenges, and current trends in the field. And the second half will be after lunch, and will be focused on 3 case studies that we had and I've worked at University of Porto. So for those who didn't met me yesterday, I come from University of Porto, and the research lab is called INESCTEC. Okay, so feel free to ask me questions if you have, and we can start. So, of course, this is always the first slide, and we, of course, are in an era of Internet of Things, data.
Sorry.
No problem.
Would you like to turn on your camera?
Okay.
Just for the people online.
I don't know if they will be able to see me, but let me see. If I'm, yeah, I can see you. Oh, that's my background at the Faculty of Science, University of Porto. I'm not in the garden. I hope the lady in the Erasmus don't see me at the garden because she. Okay, but I will stay at the garden. So we have data from everywhere, sensor data, and industry is coming to realize that that can be quite beneficial, quite productive for them in several ways. So they can easily sensorize any process, any machine. They can cross data even from technicians and operating condition on several machines. And of course, that comes with the idea of changing the usual maintenance paradigms that we have at the industry field. So back in the old days, whenever there were not so much data, and still in many industries, more traditional ones, what they do is a kind of whether a corrective maintenance or a preventive one. So in our cars, that's basically what we do, right? We either send him to the workshop for one of 2 reasons, whether he broke down and it's corrective, or it's in the annual visit to the workshop to do some preventive maintenance. But as time went by, data got more easily to be obtained, and then it appeared this condition-based monitoring, which is based on data that is sensorized, and is being monitored by some expert of the domain, such that, look, if one of these values fall out of this range, that might be an indicator of a problem. So there is no artificial intelligence here, just data, monitoring data, and some rules. And whenever those rules apply, an alert is triggered. So that's a little bit more intelligent, still not really an artificial intelligence itself. That's my name. So we are now in this era where we can take advantage of many sensors and many data, and with that we wish not only to infer or to see if some rule falls out of a range. We want to really infer models and patterns from that data so that we can see and spot if something is going wrong, if something is not following the pattern, that might be an indication of a failure. So we want some more advanced statistics and machine learning methods. We are here, and of course, the goal is to reach this. What is prescriptive maintenance? So prescriptive maintenance is the next step for predictive maintenance, where not only you are able to predict the failure, but you can actually set up the right set of actions so that the maintenance is made in a way of maximizing the useful life of any equipment. So it's made in the optimum time, if you want to. So I will just go through this again, but in a very superficial way, because I just explained you what this is. So basically, corrective maintenance is what we call run to failure. If you enter this field, you will learn about these key terms. That's why I'm going through them. So we just let the equipment goes into a failure, and then we take an action. Here we have regular planning for maintenance. The idea is to avoid unexpected downtimes, okay? But still we have the cost of the maintenance team, of making repairs that aren't really necessary. So it might be, and usually when it goes for maintenance, we don't know what is the problem. We just send the equipment to maintenance. Let's think of a transport or a car, and some technician will look into the old car. And if it's not so good technician, he will not spot the failure, right? So it might be ineffective in that sense. Condition-based, well, we monitor the data and we go and see if this goes out some control limits, okay? And when it goes, it signals that it needs maintenance. And predictive, okay? The idea of predictive is to be dynamically evolve with time, catch the conditions over time, and seeing if when we need to schedule maintenance or not, okay? The idea, of course, is also to avoid unexpected problems and downtimes. And this is the last one. So the thing of here, it's all very nice, but it still has some challenges because we really need for this to be effective, not only a good way, an accurate way to do asset management, but we need the maintenance systems to be very well integrated with the reports of failure and the conditions. Otherwise, we cannot assess, for instance, one of the things that prescriptive is about to do is to assess the potential outcomes of different actions so that it can recommend the optimum ones, okay? So this is still a challenge because it's very difficult to have these maintenance systems very well integrated with the condition or asset condition, okay? So this is about what I have told you, but putting more in a tabular way. So we are going today address this part. And of course, regarding the effectiveness of this, what each one of these approaches depends on different things. In our case, of course, if we don't have good monitoring data, we will not able to detect anything, okay? We are only relying on data. So the first thing is, how can we establish the asset condition, so, or the equipment condition? So first of all, we need to understand some concepts, and the first of them is the health indicators, and that can only be established by some domain expert. What really indicates the health of some equipment. What kind of things should measure that condition? Then we need to establish what is normal. What is the normal operating condition of this equipment? Okay, and then we need to understand what is a fault. A fault is not necessarily a failure. So a fault is something that it's very different from what is expected from the normal behavior or normal operation condition, but might be due to chance. And that happens a lot on sensor data. On sensors, it's easy to have this spike that doesn't mean anything. For instance, if you have an optical sensor and some fly goes by, the optical sensor will do a spike because something went through the sensor, and that does not really represent any fault of the sensor at all, okay? But that might be an indication of a failure also, okay? And a failure is a permanent fault, okay? Something that really interrupts the functioning of the equipment and its ability to perform its function. So that's a failure, and that's what we are willing to spot here. And then we have, for one of the subtasks of predictive maintenance that I will address here, is the part of how to measure the degradation of an equipment, okay? We can actually use that for one of the tasks, but we need to have some way of measuring how is that equipment being degraded over time. Here is a curve that, if any of you have gone through this topic, for sure comes across this curve. I didn't ask at the beginning, but did anyone here ever worked in the field of predictive maintenance? Yes or no? No? Okay. So this is called the PF curve. And this illustrates very well all these concepts, how they fit together. And we have here the time and the asset condition, okay? And what we have here is the installation of the given asset. And we know that over time, the equipment will function until up to a point that it will break down, okay? This failure here is the point from which the equipment can no longer operate, okay? Okay, the corrective maintenance will act somewhere here, the preventive somewhere here, but we want to act somewhere here. So we want to be able to deal with this PF interval. P is the point in which the failure starts to evolve, okay? So F is the point of failure. So we want to do our maintenance as close to P as possible, okay? When it starts evolving, we should trigger an alarm. So to finish up these first concepts, of course we can, I think it's easy for you to understand why this is beneficial for industry. So the mechanical pieces are expensive, typically, so they would like them to be functioning as long as possible without making any disruption on its operating conditions or its functioning, nor to have a chain reaction in other equipments, okay? And regarding predictive maintenance, if you start and see some of the surveys, you will not only see data-driven approaches. There are some physics model-based approaches which rely on this physics behavior, known model behaviors of these equipments, and based on those laws of physics, they can also predict something, okay? What we will address here is not related to physics nor model, it's not my area, but we will rely only on data-driven. There are approaches that combine the two and actually work very well, okay? But we are now just taking advantage of data and see what can happen. So it makes a lot of sense for Industry 4.0, mainly because of competitive issues, okay? And we can easily set a lot of sensors. Sensors are quite cheap at the moment, and we can measure almost anything, okay? So we can easily get data, and that's one of the things that we need to account for when we start to deal with data-driven predictive maintenance, is that, first of all, we are in a streaming scenario. So we are capturing data over time. And what kind of data over time can we collect? First of all, we can have this one, which is basically the sensor data, the raw sensor data, which is multivariated time series. Okay. Then we can also, in simple situations, have the log data. Okay, some equipment, some machines actually have a log, and we can take advantage of such log. And lastly, we would like to have, and this is not always available, but ideally, we would like to have the report of maintenance. Okay, when there was some maintenance, some guy writes what was the problem, what he replaced, when was the failure. That would be very important for addressing this problem properly. Of course, there is not always this all this information, so we have to sometimes deal with what we have, and that's it. In the next part of the tutorial, I will show you an example where we actually have all these, and another ones that we don't have this. So, of course, this relies on data. The more data that we have, the better. There is something good or interesting about this, being relying only on data. Sometimes the collecting of a set of data and only looking at data, machine learning methods or statistical methods, in some cases, can really spot complex patterns that are not easy for a human to spot, okay? Sometimes there is some interactions, collect a bunch of sensors, and through machine learning, we can easily, or at least we can find some complex interrelationship between these sensors, which it's not always possible for an expert. It can be a very good expert, it can have a lot of experience in the field, it can make sense to them, but it's not always so easy to spot that that is causing that in combination with that, okay? So please, if you have questions, interrupt me, okay? So here is another curve that you will see if you enter the field, which is related to the cost. And basically it's the place where predictive maintenance relies within, if we look at the cost of corrective maintenance versus the cost of preventive maintenance. So these are two opposite fields of the cost. So in corrective, we have a lot of costs because we have to replace the equipment. But if we have also excessive preventive maintenance, we might have also a huge cost because we are sending the equipment for maintenance, and maybe we are replacing pieces that are not necessarily or do not necessarily need to be replaced. So we want to be at this optimal zone, okay, where we have this trade-off. That would give us the opportunity to both shorter workshop visits, because if we tell the technician that the problem is with this component, rather than just check if it's everything okay, he will go to that place. He can do better planning, reduce the number of incorrect repairs that happens in our cars, for sure. They make some repair, it doesn't work, so we have to go back to the workshop and see, and of course optimize these maintenance intervals, okay, as we need. Applications, there are more and more and more, okay, but I chose these 3 ones that I think they are very active at the moment, okay, in the energy area. Of course, in industries that are connected to energy are very interested in anomaly detection in electricity meters. Even sometimes it's for fraud, not really for failure, but okay. The failure prediction of connected heating systems. They are quite complex network, these heating systems of cities in the Northern Europe, for instance, and they want to spot if there is going to be a failure at some point. In the industry area and manufacturing, of course, the disruption of production has a huge cost for them, or malfunctioning pieces. So they want to be able to predict if something is going to fail. For the environmental hazards of risky industries, such as the ones that perform the extraction of oil, they want to minimize the risk of having an environmental hazard. And in the transport area, and for planes, it's been going on for much more time because it's a more risky and impactful area. And now it's becoming to get more common in public transport area. And the case studies that I will talk about is on public transport area, okay? So this is still an odd topic because of all the reasons that I have told you, because as we evolve, the systems get more and more complex. So more things interact with each other, and it's unfeasible to think that we can have a particular diagnosed for every single possible failure, okay? Or design a possible diagnosis. And sometimes with the data, what we think we know turns out to be wrong. Sometimes what the expert think he knows, sometimes the real data will tell him otherwise, that something is working or not working for different reasons. But of course, we again are in a streaming scenario. We need continuous learning, lifelong learning, because one of the things that I learned about these equipments is that they are not supposed to work always the same way, okay? They evolve with time, their function evolves with time, and that makes the problem more challenging because we cannot just learn one model and hope that until it breaks down, it will follow always the same model. It will not. Because of this. So first of all, we have these internal conditions that evolve with time. That is kind of expected, and it is explained by physics. And also, we have these external conditions, okay? These external conditions, such as meteorological ones, geographic position, all of this affects the functioning of equipment. An equipment in the south of Portugal or in the northern Europe are affected in different ways. They are mechanical, like the passenger's doors of a train. The weather conditions affect a lot the way they function. That doesn't mean that they are failing. It means that they are subject to external conditions. And that's a challenge to know if we are really in a case of fault or just external conditions. And the other challenge regarding the domain is that we might have low quality data. What does this mean? It means that, okay, we start sensorizing an equipment, but the people who will choose what to sensorize might not be keen on that. Or what I mean is that probably we are not measuring the right things. Okay, it's up to the technician to decide what to be sensorized. We cannot sensorize, well, of course we can sensorize everything, but sometimes he has to choose, and sometimes it will not really help us into spot the relevant process of the equipment. The other thing from the domain perspective, because I'm going to tell you about domain challenges and tradition and machine learning challenges. The other thing from the domain challenge is that we are looking for indicators of failures, right? And how can we get data from those failures? We have 2 or 3 options. One of them is just letting the equipment running into a failure, okay, so that we catch that failure. Of course, that has costs, because we let some equipment run into a failure. Or we can do some kind of fault injection, so that's to simulate a fault. That happens on a very well-known data set from NASA, that they have injected these faults in order to be able to learn what are the faults. But of course, this has a problem of not being able to embrace all situations. The faults were chosen to be injected. And it's hard to, know if those faults really will be real life faults, or the ones that would come up and we want to learn from. So most of the data that we are going to collect is not going to be really representative of what we want to learn. Okay, we will have good examples, at least, or we hope that we would have good examples of the normal condition of the equipment, but we will have few examples of a faulty one. Okay. The other thing related to the part of collecting data is that even if we gather faulty data, either by running into a failure, either by fault injection, we need to know from the domain 3 things. We need to know what is the appropriate time window to consider. So it is unfeasible to think that we should take into account all the data from the beginning of the equipment, okay? For several reasons. One of the reasons is, of course, time complexity. And the other reason is that, as you will see in second part of the tutorial and one of the case studies that we did, is that we should keep moving as the time goes by with the evolving operating condition of the equipment. So, but how far back should we go to be with the updated operating condition? how much data back do we need? The other thing is different equipments change their functioning at different rates, okay? Some thing in the transport area for sure has a different behavior from some energy field equipment. So how often should we relearn the model? How often these operating conditions should be taken into account? 1 month, 6 months, 2 hours, it depends, okay? And the final thing relying on domain challenges is how much time do we need to consider to make those predictions useful? And what are useful predictions? Are predictions that are in time for having such human intervention that avoids the downtimes. Otherwise, it's not useful. So imagine that you want to, let's take the car again, example. So you would like that before you leave your home and going to work, if something is going to break down, you would like to know just before starting the car, right? Not at the middle. So if the car tells you, okay, in about 5 minutes, your car is going to stop. There is no usefulness on that prediction because you are not in time to making actual intervention. Of course, this from the car is a very dummy example, but in the industry, this means a lot, okay? So we do not want downtime in the machines, so we need to know from the domain how much time in advance do we need the prediction to be made. Okay. So the second half, it's now on machine learning force. So far, I have told you about these main concepts of the data-driven predictive maintenance, the domain challenge that are not easy to address, but also from the perspective of machine learning, we have a lot of challenges, okay? And I would say that our major work, whenever we are dealing with machine learning approaches for predictive maintenance, relies on this phase, which is going from data acquisition to meaningful features. Why? Because we have raw sensor data. Let's imagine that we have only raw sensor data, but we can, of course, have as I told you, log data and the maintenance reports. But let's imagine that we have raw sensor data. We know for sure several things. One of them is high dimensionality, because sensors can collect, we can have multiple sensors and they can collect data at a very high frequency, okay? Also, another thing that we know is that the data collected by sensors would be typically of low quality. Low quality in the sense that we know that's easy for a sensor to have some noise, okay? And noise and in the thing that it's not meaningful, outliers, can have this disruption timely or for a certain period of time. So we have missing values for a certain period of time. We can have also constant values, null values. So the quality of the data itself in its raw form is not very good. And then we need a way to build up a set of features that would help us in the process. And here, from my experience, the input of a domain expert would be very, very important. So how can we aggregate data? Should we aggregate the data per hour, per minute? How can we aggregate? And more than that, what features can we build up in order to be able to capture the pattern of the functioning of the equipment, okay? So this would be the hardest or more time-consuming part of any project in data-driven predictive maintenance to get from data acquisition to features. Okay. If you have any questions, yeah.
If we get the features from sensor data based on expert sayings, are we not missing some of the potential faults that are going to occur? Because we said before that we may not be able to, well, data could have strange patterns that we could not think before.
The thing is that when we are dealing with this sensor data, we must be aware that, first of all, we don't really know if that data is reporting a normal behavior or not. That's one of the things. And even if it's a normal behavior, sometimes it can happen, those faulty things, but we don't want our models to spot that as a failure. So we have to make up our modeling in such a way that he's able to cope with individual faults, not being identified as a failure. What really, and I will show you in the second half, what really spots a failure in our perspective is a sequence of faults. When you have subsequent faults, that might be an indicator that there is a failure. But again, there is no way of being sure of that. You just rely on, okay, if it's subsequently giving a faulty functioning, probably is a failure. If it's an isolated one, we don't want our model to trigger an alarm every time. Otherwise, we would have a high rate of false alarms. And what happens when we have a lot of false alarms? We don't care. Yeah. I don't know if I answer your question. Yeah. The thing with the data is also we can have any of these three scenarios in any application. It depends. We can have a target variable in the sense that for each observation we can say, or we have the information if that's a normal or a fault, okay? Not a failure, a normal or a fault, and work on that. But of course, that is very dependent on the human expert and having maintenance reports and everything. The most frequent setting in predictive maintenance is have labels for some of the observations. And what this means that we for sure have, or for sure at least, or is expected for having easily normal functioning data, right? So we can have data for these normal observations, but we do not know what is abnormal. Okay, we don't have that information of what is abnormal. Sometimes that is the case, not because we are willing to run into a failure or not because there is no fault injection. And here we assume that we have a representative set of normal condition of the examples. Of course, that might be questionable because it's very hard to cover all possible normal functions, okay? Okay. This is, I think I would say that this is the most common one, but we have also this. This approach is like anomaly detection, where we don't have any label at all, just have a set of observations and ask the algorithm to spot, look, tell me what is in all this set of observations an anomaly. Of course, here we are assuming that the failures are the anomalies and rare cases, okay? So all these three settings are possible. And then it's like I told you before, even if we have this target variable, what does it configure a failure? So it is an anomaly. So even if we have faults, we will have few examples of faults. And that comes back to the problem of imbalanced domain learning that I have mentioned yesterday, but here in a classification context, So we have to learn from a small number of examples. So we have a bunch of examples of normal condition, but our goal is not really to spotting the normal function, is to spot the abnormal one, okay? And so we have to cope with that few number of examples of what we want to learn. And there is also this problem, is that we cannot really always rely on historical fault data, because sometimes new versions of the equipment are installed, okay, and they go to maintenance for sure, and they are deployed in different conditions. So we have to be aware that what has happened in the past will stick to the future as the ground truth always, okay? So once more, we need to keep learning and do this continuous learning and time evolving setting. And of course, I have talked about this because even if we have this normal behavior and we say, okay, this is very different from the normal, that doesn't mean that it's a failure. Not every change in the behavior reports a failure, okay? But once again, can be due to external conditions. Extreme high temperatures, extreme low temperatures, that would make the equipment function in a different way, and that it's not necessarily a failure, okay? And of course, if we don't know really what is a failure, how can we interpret the discovered anomalies? That's a current field that it's being explored, which is related to explainable predictive maintenance. So not only we want to predict a failure, we want to be able to explain it, okay? So here it's what I have told yesterday, and basically we have an imbalanced domain problem where we have few cases of failure, but these are the ones that are relevant for the domain. And that, of course, poses challenges for any predictive learning task. And why it's difficult? Well, first of all, there is no, and this is true for any balanced learning task. There is no universal way of having a definition of a failure. It's really application dependent, okay? So we need to look into the data and to the application and see what is a failure. Then we have these fuzziness on the boundary between what is normal and abnormal. It's not really easy to spot. Look, from this point, it's abnormal, and from that point low, it's normal. It's really hard even for an expert. And there is also things that happen. It's one of the things is sometimes it's just random noise, and also we cannot really spot the difference between a random noise and a failure. Well, we have to deal with it somehow. And here we have what we often will come up with, which is usually the abnormal behavior will evolve with time. And this happens in predictive maintenance because of the equipment, but you can easily see this on the case of fraud, okay? Fraudsters don't stick with the same procedures always. They want to be treated as normal, so they are always changing the way they are acting. So that is not the case of a machine, but a machine will evolve with time. Okay, so once we are settled with the normal behavior is not supposed to stick until the end in the same way. And of course, if we don't have labels, how can we really validate our model? How can we say, look, this is a failure? Well, we can do one way. We can take the maintenance report and see if it was a failure or not. And that's one of the things that we do, actually. But look, if we start to asking too much times for an equipment going to a maintenance, the guy is going to tell, okay, let's stop doing this because this costs money, and not always, they don't want false alarms, of course, okay? It has costs. So regarding the predictive learning tasks, and specifically on data-driven predictive maintenance, we have two major groups of tasks. One of them is failure prediction. It's what I have been basically talking about. And the other one is the remaining useful life. Okay. Have you ever heard about this term, remaining useful life? No? So failure prediction is expected to be a classification task in the sense that we want to predict whether a failure will occur or not in a given time frame. Okay, we have a chat. Should I answer chat or?
No, no, I will
okay.
ask you the question in the chat.
Okay. So we have this setting, classification task, and this classification task is most of the times a binary classification task. It answers the question, is the failure going to happen in the next time frame or not? Then we have another group of approaches that you can find in the literature, which is predicting the time left for the equipment to keep working before it goes into a failure, okay? Or before it should be replaced. This is predicting the remaining useful life of the equipment. And in that sense, is a regression task. We are predicting the time left for this equipment, okay? So our model, instead of saying just yes, no, is going to be a failure, this model will say, okay, we have, let's imagine, 10 more days, 9 more days, okay? Of course, as you can imagine, this is a little bit more hard as a task than that one, okay? But it's used, and is used many times relying on those physics models that I have mentioned to you, because these physics models can actually compute the degradation of the equipment over time, and that is very related to the remaining useful life. Okay. In the case of failure prediction, what we have, so my mail is keeping, I had to turn off the email, but we want to predict if it's going to be a failure, and we want to predict in some time frame, okay? And our problem is to say if it's going to be a failure or not. So it's a binary classification problem, and we are in a streaming scenario. So we will have signals, subsequent signals that will tell us that is it going to be a failure in the next time frame? Here it's no, no, no. And then it starts saying yes, yes, and here it's a failure, okay? And then it goes back to no. So we have a binary setting where we have these true positives, false negatives, and this is the typical confusion matrix, right? So my question is, how do you think we can measure how effective is a prediction model in this context? What measure can we take from this confusion matrix that will tell us that this model is good at predicting failures? True positive rate, for instance? Yeah, like recall. Yeah,
You have to calculate the precision.
the precision.
Using, for example, the rock curve
Yeah,
or
yeah, that's two possibilities. My question is, can we use accuracy? What do you think? Accuracy is basically the rate of correct prediction of all the predictions. Do you think that we can measure the effectiveness of our model using accuracy? Why? Yeah, so if we use accuracy, okay, and if we have like 100 cases, only one of them is a failure, and we always say there is no failure, our model will have 99% of accuracy, but it's useless, okay? We don't want to focus in the two classes performance. Our focus is this one. And this one is much more, it's more rare than the other one. So accuracy that takes into account the two classes in the same way will not be a fair way of measuring the effectiveness, okay? So then we have what we need to define, which is not so straightforward. So in a batch setting, we know when it's a true positive or a false positive or whatever, okay? But we are in a streaming scenario. And we need to define what is a true positive. First of all, let's start with a true positive. So a true positive is an example where we actually predict a failure in time to be corrected, right? So we have here an alarm, and this alarm is done with enough time for a human intervention to occur here so that this failure doesn't happen, okay? That's the definition of a true positive. And regarding a false positive, the false positive is done in a way that in some way the failure is starting to evolve. So the maintenance team would spot the failure. Otherwise, it would be useless. It's like saying the next year you are going to have a fail. Okay, good for you. But it's not useful, okay? We need to get a positive, an alarm, but only when that failure starts to evolve, not just any time before. Otherwise, it will be useless, okay? What is not a true positive nor a false positive in this streaming scenario? This is not a true positive. Why? It's like I told you before, it's not given with enough time ahead to be able to correct the problem and do not have the failure. It's like going in a bus and the driver gets the alarm that on the next 5 minutes, the bus is going to break down. Okay, but that's not useful because the bus is going to stop anyway. So you have to let people out of the bus, change the bus, everything. So that's not really a true positive in the sense of failure prediction, okay? And here, it's not a case of false prediction or false positive, because imagine that something went wrong here and the bus went to the maintenance and it's being inspected by the maintenance team. It's not worth to have these alarms keep triggering because here they are no longer useful. While they are being subject to maintenance, these alarms should be muted, okay? They are not used here because it's already being spotted here what happened. So this is not also a false positive, okay? The last thing about measuring this effectiveness of these models is what should be counted as a true positive or false positive. So we are in a streaming online scenario. So it is expected that subsequent alarms are made until the failure actually occurs. But when we are validating our model, do you think that this should account for 3 true positives? They all refer to what failure? This one. Okay. So it would not be fair to say that our model made 3 true positive predictions because they report to the same failure. So if the system works well, the alarm will keep triggering until the failure occurs. So we need some way of grouping together subsequent alarms so that they are count for 1 true positive regarding that specific failure. Okay, this is 1 true positive of our system, not 3 true positives. And it works in the same way around for false positives. We should not penalize our model too much in the sense that he is giving here a false positive and is keep triggering these alarms, but it's also false positive. But if they are subsequent, we should aggregate them somehow and count that this represents a false positive because it's too early for any failure to be in the time frame that is expected. Okay.
How do you measure that it's too early?
Yeah, that's a part of the domain challenge. Well, for instance, in Metro do Porto, they tell us that they want, before the metro goes into the operation, they want to know, for instance, in the point line machine, there's a lot of failures in the point line machine. They need that 2 hours before to know if there is a failure in order to fix the point machine. But if you tell them, and this was a guy from Metro do Porto, if you tell them like 1 day ahead, the maintenance team will not go there. Okay, so probably it told us at least 2 hours, and at maximum before the train leaves in the morning, in the early morning for that line. Okay, it depends a lot on the domain application. So this is what I have told you. Standard performance metrics such as accuracy or error rate do not work well here because of the imbalanced. So this is the case of what I have told you, that you can easily obtain a 99% of accuracy, but this model is useless. Okay. So the focus is on this small subset of cases, which is the failure. And any average is not a good idea. So what we want is to focus the performance on the positive class, which is in this case the failure. And so all those measures that you have mentioned work here: precision, recall, false alarm rate. Most of the industries of the clients, as they are looking for benefits in terms of costs, they are mostly interested in the false alarm rate. Okay, because they don't, the false alarms for them have a huge cost, which is going to the maintenance, putting a maintenance team, looking at the equipment. So they really want to minimize the false alarm rate. And also a common name in this predictive maintenance field is to call the false positive rate the imposter pass rate. Okay, the ones that really were not predicted as I think this is switched. This is false positive and this is false negative. Okay, so the false alarm rate is the false positive rate, and the imposter pass rate is the false negative rate, which is a false negative. The train keep working and we didn't spot it. Okay, but you can use a lot of them. F measure, IUC under the PR curve, and so on. There is also the possibility, not always available, but for instance, with how do you say, the wind aeolic turbines. They have in that industry, they have these really measured costs. If you have access to that, of course, the measure of effectiveness of your model will be more precisely measured and in a more meaningful way for the clients, which is, you know, how much do you save by capturing a failure? Do you know the cost of an inspection, which is the false positive? Do you know what is the replacement cost of a? So if you are able to measure that, or if the domain expert gives you that, that can be complemented with the remaining binary classification performance metrics, okay? This would be meaningful for the client, okay? And you can show them, look, you are going to save this by using this model, okay? But it's not easy to obtain. Even sometimes the experts don't really know how to answer to you about this. It depends on a lot of factors. So to finish up, I'm just going to talk about the remaining useful life, and then an approach of deep learning. And we wrap up the morning part, and in the afternoon, I will talk about case studies. So the remaining useful life, as you remember, is a regression problem. I want to predict the time left until the end of the useful life of an equipment. So it's like I told you before, okay, it spots here that the remaining useful life is 10 more days, imagine. And it keeps decreasing over time as you reach the known failure. So here you need more fine-grained information because we need to measure somehow the degradation of the components. And that's not so easy also to have, but if you get features that give you the amount of the degradation of the components, you can build up a regression model that is going to predict the remaining useful life. And this doesn't need that hard threshold for is going to happen here, okay? The idea of time to failure, it's a linear relation, okay? So as time goes by, the time to failure, it goes decreasing. But we have the remaining useful life. And do you remember the PF curve that I showed you at the beginning? So that is a remaining useful life curve. So the actual shape of a remaining useful life curve is something like this. You have on the X, the time, and on the Y, the equipment condition. And we know that the equipment is functioning well up to a point when it starts degrading. And from that point on, it will run into a failure much more in a steep way, okay? And we establish a failure threshold. We, usually the domain expert, which is the minimum acceptable condition till the end of life of the equipment, okay? So if we are here, our remaining useful life is this. As we keep approaching the area of the failure threshold, the remaining useful life is going to be shorter and shorter and shorter. Not always we have access to the end of life, And when that's not the case, some works use the mean time to failure, mean time between failures to have some kind of estimate when should be that threshold established, okay? So they know that this equipment will, it has to be replaced every year. So you set the threshold over there if you don't have the exact information on end of life. Again, we can use standard error metrics, and most of the times they are used. Again, because imbalanced regression is far less explored than imbalanced classification, and they are used. But here also other metrics were proposed because of this non-uniform importance of the values across the domain. Okay, so what do you think? The values here will be more, making an error here will be more serious here or here? If I make an error of 2 here and an error of 2 here, what do you think would be the more serious one? The one that is closer to failure or the one that is closer to the one that is closer to here? No? Look, if I imagine that here is still functioning, okay? If I make a huge error here, or 2, like imagine 2, I might say that it still has 2 days to work, but I said it has like 5 days. So it runs into a failure, okay? And if I do same 2 days error there, of course, it's not ideal. What we want is a good prediction, but it's not so bad. Here we can actually run into a failure. Yeah. So there is also the question whether should we account for the metrics in a standard way, so all the values count the same. And what happens is that, as I told you, the performance near the end of life should be more critical, the performance of the model. So we can have different alternatives to assess the performance of these models. One of them is to have different criticalities associated with different stage of the process. One of the ideas that was proposed, not 2021, it's 2012. I can then afterwards correct the slides. It was proposed by a challenge in prognostics horizon or related to the remaining useful life, which is the exponential transformed accuracy, okay? Basically what this measure does is to distinguish not the place where the prediction is made, but assigns different importance to over predictions and under predictions. Do you think that in this case, it's more serious to give an over prediction or an under prediction? Under or over? Didn't understand. What is more serious? It's a trade-off.
No, it's undetected failure is more serious than detected failure.
Yeah, because yeah. So if we do an overestimate of the remaining useful life, we might run into a failure. So we are saying it's that same thing. So if we are saying that we are committing an error of 2, and we say, okay, we have 5 more days of remaining useful life, and it will happen before. So it will be more serious than saying, look, I have more 5 days of work, but I'm predicting that only 2. So it should be accounted differently, even for the same magnitude of errors, if it's been made an over prediction or another one, okay? And that's the formula they came up with, okay? And there are a few alternatives to this. This is just to show you an example. And basically what they do here, they call it like an accuracy because it's in between 0 and 1. And they have the error rate here, okay? So basically you achieve the maximum accuracy if the error is 0, okay? If you do late predictions, the accuracy decrease is much more faster than if you do early predictions. It looks at what type of errors are you committing, positive ones or negative ones, basically overestimation or underestimation. Basically, the intuition is this, okay? So it's an asymmetric error function. And then there is another one that is quite, yeah?
You have like fixed factors like 5 and 20, but in reality, you could moderate that with the cost of undetected failure and the cost of overtake, like useless maintenance.
Yeah, you can adapt all these fixed values, adapt to your domain. These were proposed by the authors for a specific challenge, and they achieved good results with those specific values. And they have proposed another measure such as this one for another work. Well, that depends a lot on your data. And I don't know why they chose 5 and 20. Probably they have done some tuning with the data challenge, but of course. But the main idea is to have these exponential functions that are different in one side of the errors or others. And then there is another one. I have at the end the reference of papers, the paper that proposed this and the paper also that mentions this. This is interesting in the sense that you have this prognostic horizon. So basically you want to test if the predictions satisfy a given prognostic horizon. And that means that you want to know if your predictions fulfills that time horizon, and you account for the first one that is able to account for that horizon. And in this sense, you want to know what is the first observation such that you achieve an error bound smaller than this alpha, okay? And what they use this for? First of all, they see if that's that is accomplished, and then I will not enter the details, but I think that this graph is very insightful. So first of all, they see if they fall in this horizon, and the other thing they account for is the error margin that evolves with time. Makes sense, right? So here, the error margin is larger, and as you move down, the allowable error margin gets narrow. Okay, so basically they see if your model is within this margin, okay, to measure the effectiveness of your model. This is called alpha lambda accuracy, but the details you can look in the reference. Okay, this is the main idea. So this predict.
Sorry.
Yeah.
How is it possible that the predictions are going up sometimes according to time?
This is a toy scenario. Okay, so here what it's intended to show is that, okay, this will be an acceptable prediction in the sense that it's on this error margin. That will be not acceptable, and that will be acceptable also here, not acceptable, and here as it goes here. You measure your predictions according to the place that you are and the margin that you have for the error, okay?
There is no relation between the predictions at specific time step T and the previous predictions?
The previous predictions, no. I think they evaluate like this.
Okay.
Okay, how is the model coping with this? The set of predictions that he made. Okay, is taking into account an accuracy that is based on it. Basically, I think by using accuracy, they are saying, okay, this is a true positive, false positive, or something like that. Okay, so but they narrow the margin of allowable error, and of course they count. They have always this horizon. So basically, this is the idea. Also, remaining useful life is a harder problem in comparison to failure prediction. It needs more information, more precise information. Of course, can be more useful for the client. It's not such black box as saying it's going to be a failure. It tells you more about how much time you have left for the failure to happen, but also demands more information. You can, of course, turn a remaining useful life problem into a yes, no, in the sense of failure prediction, okay? So to finish up, data acquisition, data preprocessing, building a model. I didn't spoke about building a model because many models exist that you can apply, and I will talk about one specific one, but and then evaluation and exploitation. So these are the main steps for a machine learning process. And okay, in data acquisition, we have expensive in the sense that you have to sensorize, and it's manual in the sense that you have to have these old sensors and acquire all the data. The data preprocessing, which is boring, time consuming, and I would say that it's the most crucial part of the process. Building a model, it's not the hardest part in this thing. And the hardest part next is the evaluation, the proper evaluation. And of course, if you want to explain your predictions, is even an open challenge problem. Many, if you go to the state of the art, many of these algorithms have been used, these standard ones, okay? Regarding if it's a remaining useful life or a failure prediction model, even if it's unsupervised, like I told you at the beginning, so you can just get a bunch of data and see what doesn't fit the normal regime. So you can use something like k-means or hierarchical clustering. But the current trend now is to use deep learning. And why? Deep learning in this specific case, it can help a lot in this stage, okay? The data preprocessing. It can find you features that really help in the accuracy of the models. It has, of course, some drawbacks. I don't like it because it's a too black box model, but the truth is that it gets very good results. And one of the things that we are going to, and we are trying to do is, okay, let's use the deep learning models, but let's first do some feature engineering. Let's first see what we are giving the model. And then afterwards, let the model make the predictions. Deep model are very good with high dimensionality problems, and try to explain how did you get from these features to these outputs. So that's like using a post-hoc explanation, okay? But deep learning is the trend, mostly because of the amount of data. We can get process a lot of information, and with big data, it gets very good performance. And basically, the main thing is that deep learning would do for you this feature extraction. It would end up extracting the features that are more meaningful for the classification of the classification task. In this sense, these are some of the deep learning approaches that you will find on data-driven predictive maintenance surveys, many of them, but I will focus on the autoencoders. So have you heard about the autoencoders? Yeah, okay. So basically why autoencoders are here used? Because we want to take the normal observations and learn the concept of the normal pattern, okay? So by using an autoencoder, we can make the network learn to encode and decode those normal observations. And with that, we know that if we supply something that does not cope with that normal operating condition, the network will struggle to reconstruct the input. So the algorithm that he has found for coding and decoding will no longer work as well, okay? Because it doesn't follow the pattern that he has learned. So based on that, we can do some kind of anomaly detection. Okay, we can say, okay, if the reconstruction error is too big, probably it's because the observation does not follow the normal pattern that the network has learned. So we use autoencoder to detect these deviations that can constitute failures. Okay? We also use long short-term memory, LSTM's autoencoders, because we can take also advantage of time dependency. So the standard autoencoders, deep ones, I have used also shallow ones without deep learning, but the standard do not take into account this time dependency in encoding and decoding process. If we use LSTMs, we can ask the same thing to encode and decode, but in this step of encoding and decoding, it uses this time dependency of the different time series of that we gave them, okay? If we give successive time of sliding windows, he will learn to encode and decode them in a way that it takes into account the time. So in the second half, I know that you need a break. So after lunch, I will talk about 3 case studies. And one of them, I do not use deep learning. And in the other 2, we use autoencoders, deep autoencoders, and the third one, LSTMs. But we do some kind of feature engineering first, okay? So the next steps regarding predictive maintenance will be the explainable predictive maintenance, okay, which is currently open research topic. How can we explain that failure has happened so that we can help to come up with a new maintenance plan that will be more effective? And of course, the ideal setting is the prescriptive that I told you at the beginning, which basically combines the predictive maintenance with prescriptive analytics, but depends a lot on data that usually is not available, which is the integration of the maintenance systems very well made with the condition of the equipment. We usually don't have that, but of course, the idea is to maximize the useful life of any equipment. And if you are interested in this area, this applies to many, many settings of machine learning, not only supervised and unsupervised, but for instance, transfer learning is active. Why? Imagine that you are in a set of a bus, a Volvo bus company. You do not want to learn a model for every single bus. You would like to learn a model for a bus and then transfer the model to other buses and see how it copes with that and just adapt something. And that happens also in equipment in the industry, okay? Active learning in the sense that you can ask for several observations and ask for the domain help for that. Feature extraction, data fusion, because some approaches now are trying to extract features from audio of the equipment or images, or, okay, you have plenty of things, and of course the explainable and interpretable models. So the idea is that if we come up with this, we will end up with a better design of the equipment, maximize the useful life of the equipment, and of course reduce the amount of waste that we have nowadays from electrical and electronic equipment. That is a problem nowadays, okay? So if we maximize the useful life, that's better. And that's ends up. I have put here some of the references of the papers where I have based myself, okay? But I have other references if you need. So I just point some of them here. And as I told you, in the next half, if you are willing to listen to me again, is the case studies. Is basically show 3 case studies where we have applied data-driven predictive maintenance. Not always as successful as we would like, but of course this is a challenging problem. So just one. Thank you. I don't know if I should answer. What are the applications of predictive maintenance in information systems? Information systems like well,
data center.
Probably that they are, it depends. This applies to many application fields. Of course, it's relying on the domain knowledge on that thing. For instance, in telecommunication, I can imagine if something breaks down in a point where there's no redundancy, and that makes that short or interruption in the telecommunication, that would be a very important problem to try to predict in advance if it's going to have some kind of disruption there. This is especially relevant when you do not have redundancy. In the sense that you do not have an alternative, for instance, or you say that supply machines, I forgot the name. When the power goes down, the electric power goes down, your server has a redundancy backup so that you are not going down. I forgot the name of it. It is a well-known device. But whenever you don't have such redundancy, this is critical. And the other, I wonder if we can use PF curve to force the alarms to be issued in turn. The PF curve is just the remaining useful life of an equipment. So we can, of course, if we have that failure threshold, we know how far before we want to make the prediction, the most early, the better, but we do not want to be afterwards. And that is the problem of making errors, different errors in different ranges of the PF curve that should account differently.
There are some applications in cybersecurity, for example. Some
cybersecurity, it's more related, I think, with anomaly detection, not such as failure in the sense if they are sensors, but some of these things apply to cybersecurity because this is imbalanced domain learning. Yeah. And imbalanced domain learning, I think in cybersecurity, there is also this sequence of commands which are strange, and it cannot be spotted as an isolated attack, if only one comment, but the subsequent comments made by some hacker that might be, and in that sense, it's related, and also evolves with time because the hackers do not want to be spotted right away. So I would say that some of the techniques apply, even though it's a broader field of anomaly detection in streaming.
Okay. Rita has one question about the business case.
Okay.
This afternoon.
Yeah.
Okay, in this context, I have a question.
Yeah.
The cybersecurity application. Can we say that your approach can be applied on the prevention of distributed denial of servers in order to estimate the time so that the server will,
Probably, yeah.
resist against the attacks and know when our servers will go down.
I think that would be interesting to make that that parallel, but you need, I would say that you need to have some measure of the degradation of the survival of the server until it
Yeah,
gives a denial of service.
It's possible since we have a lot of parameters and data from the server, from the network, about the degradation of the servers.
So that would be, I think that would be applicable. Yeah.
And my second question is about the cost of the false positive and false negative.
Yeah.
So the cost is very important when we evaluate the precision of our system. So how could you estimate this cost, and how can we take this cost into consideration when we calculate the accuracy of our system? So a priori we cannot know what is the cost. So how can we calculate this sort of cost or estimate it?
So if we don't have these measures specifically, which is kind of difficult to obtain, I would say, from my perspective, that a measure that combines two approaches would be better at this. For instance, F measure would combine precision and recall. That means that it measures in one hand if all the predictions that has made are really true and are not false alarms, and on the other way around, if you are able to capture all the attacks that have been made. So you want a balance between the two, and that's precision and recall. Okay, so basically we are measuring the accuracy on the positive class based on the all positive examples, how much you capture, and based on the ones that you predicted as positive, how much of them are really positive. Or you can use the area under curve that put in relationship the recall and the false positive rates. For some domains, it's more important to have a small false positive rate rather than being with precision, for instance, even though they are somewhere related because the precision takes into account the number of false positives. But here in the IUC and the ROC curve, you account more explicitly. You want to minimize the false positive rate and maximize the true positive rate. So you want to be the highest possible in the ROC space. So from my perspective, if you do not have this information, because it's hard to obtain, I would not rely on a single measure. I would rely on a combination of measures, and that can be F measure, IUC under ROC, IRC under the precision and recall curve, and there are others like balanced accuracy, if you want also to take into account the accuracy on the negatives, but this balanced accuracy takes into account the frequency of the positive and the negatives, or the J-mean or MCC, which is Matthew correlation coefficient. So all those measures that are focusing on the positive, okay, and some way take into account the negative, but do not let them bias by the negative, which are far more frequent, such as accuracy.
Could you give us another application, for example, to like approach, for example, in medical machines, some factories, for example, where can we apply this?
Well, we have lots of applications. In the medical field, it is of highest interest, but it's very hard to get the data. So for instance, it's very important for them to know how much time this equipment is going to function, or with that, which is monitoring some health of some risky patient. But we have a lot of issues regarding the data. People, for machines, you can use the data from machines, they don't mind, but for humans, it's not that the case, okay? But it's being applied a lot on, of course, the transport area, in planes for many years, more than we ever know, because they are a risky area. The public transports now are starting to use the manufacturing, and also here, whenever you are performing risky operations that might cause environmental hazards, for instance, such as the extraction of oil or other things that might cause an environmental hazard, which has a huge impact. They are really interested in such things that try to predict when it's going to be a failure. And in the energy area, the northern countries have this complex network of heating systems, and they want to, and they have these failures they want to be able to spot beforehand, to not have this disruption and people churn, like in telecommunications, okay? But here, I think there are two very near areas, which is this failure prediction and fraud prediction, okay? Fraud can happen also. It's caused by a human. It looks like a failure and it's not a failure. But the fraud in nature is a different problem from the fraud is an intentional failure, okay? There are some things that can be applied to both, but probably not in the same sense. The machine is not failing by itself. Just to finish, a person from Poland that is working on failure prediction was working on a steel factory and coal, extracting coal. And they wanted some data predictive maintenance because they had some disruption of the machines. And they start to do the sensorizing, and then they understood that there were some workers that made the machine to fail so that would not have to work the rest of the day. Yeah, and that was reported as a failure, and they said, look, the machine has failed. But then they found out that it was the worker that they know how to make the machine fail. Oh, that happens also in TV services that we have, telecommunications. I learn a lot from when someone has a problem. For instance, in your building, you have the same TV box central for your building. And the guy that goes there earns some money every time he goes to the maintenance, okay? So what he does when he fixes one client is to make a small change in another client out of same building so that he will come back to the same building. So, but here we are dealing with fraud.
And in this domain, for example, actually how predictive maintenance is treated. There is no solution for the predictive maintenance actually in this domain.
For instance, in this domain, which I have been working on, most of them still rely on corrective or preventive maintenance. So they do the maintenance when it ran to a failure, or preventive because it's a timely scheduled preventive maintenance. So they are starting to sensorize everything and getting the idea that that could be a huge benefit for them. and I have worked with UK trains, a small amount of data, Metro do Porto trains data, and Volvo bus data. And even though we were not able to predict as soon as they would like, we were able at least to detect the failures. And that is a first step towards, for them, that they do only corrective and predictive and preventive maintenance is something new.
You didn't talk about the probabilistic model.
Yeah. In the remaining useful life, you can have also like a survival analysis. And for that perspective, instead of having this RUL curve, you have a probability curve, which is more like the probability of having the failure. It's more like this. So it goes up as you approach the failure. But that is one of the approaches that is done regarding remaining useful life, is to do a survival analysis. There are a few people that use survival analysis techniques applied to the remaining useful life. Okay, but in that case, you have to have an estimate of the probability. Okay.
By a model like the gamma model, for example?
I don't know, because I don't work on that survival analysis, but I know that there are a few works on that. Here I'm mostly working on the regression perspective. And from the regression perspective, we are working with the time until a failure. And still it's difficult to have this equipment condition that allows us to estimate the time to a failure. But yes, there is survival analysis that also can apply here. And they do that a lot on the medical field.
Okay, thank you.
Thank you. Thank you.
Thank you very much.
So should we go for lunch?
Yes.
Yes.
Yeah. Please.
I will stop recording.
Okay, thank you. So you can click on pause also. This afternoon, can you start at 1:30 so that people have time to eat?
Yeah.
So we have 1 hour for the application this afternoon.